Hello all. Today we are starting a new section of Accentus and it is called half a dozen. Now actually this is a section where we will be doing 6, that means half a dozen sums, and will understand the most of the concepts of a chapter through these 6 particular sums. And that is my motive, and that was my idea, that okay, I can do this and it will serve my students as a quick revision guide. Okay, so today's topic is rotational motion, and here is the first problem coming in front of you, and do copy this problem in your classwork and then I will solve. Okay, here we go. So we have to solve this problem, and not only we have to solve this problem, we have to identify the uniqueness of this problem, because the uniqueness of this problem will solve maybe 100, 500 or maybe 1000 other different problems which will be based on the concept that this problem belongs to or that this problem has. Okay. So what they asked us is very simple. We have a sphere on an inclined plane and we have a small plate or wedge, whatever, and this sphere is not falling down because of this particular block, and they have asked us that what will be the minimum height for this block so that this sphere doesn't topple or this sphere remains in equilibrium. This is the concept. Okay, so if this is the concept, or if this is the question rather, I'm sorry, so we have to solve the problem based on these given informations. What are the informations they have given to us? They have given us the radius of this sphere, they have given us some height of this block or wedge which is keeping the sphere not on the verge of falling, it is at equilibrium. Now, so here is the diagram. Can you see that? We have drawn the diagram. This is the inclined plane of inclination theta. This is the sphere, and this line is the weight of the sphere, that is mg. If the mass of the sphere is m, then it is mg, and weight, you know, it's always vertical irrespective of the position or the orientation of any extended body. Great. So now we have to understand what is the concept, what is the uniqueness of this problem, because that actually can help us to solve a lot of other problems where these type of concepts are hidden. So let us identify the concept. What is the concept here? We have already said that weight is always vertical. Now tell me one thing, why the sphere rolls, or why this sphere actually slips over an inclined plane and it falls down? The reason is weight. The component of the weight, that is mg sine theta, you know that, and there will be mg cos theta, that will actually applicable for the time when we have friction. They haven't mentioned anything. So we have not taken any components. We know that due to mg sine theta, this will have a tendency to slip, or even if the friction or other forces can provide necessary torque, then it will show a pure rolling and it will roll down the inclined plane. These kind of problems we have solved. I mean, in each and every book or textbooks that we have, they have these kind of problems, but what they don't have is this. Now we have kept the sphere with this block, and they have said the height of the block is h, and we have to find out what is the minimum height for which the sphere doesn't slip or roll or it doesn't fall down. So it is under equilibrium. This weight is always acting vertically downward, and we see that through the center of the sphere, when this weight acts, it is intersecting the sphere at a particular point, and that point is very, very interesting, I'm telling you, because this intersection, you can see here, you can see this point. This point is the point of contact of the sphere on with the wedge or the block having height h and this point of contact, the sphere will come and rest on this block because of the weight. It will try to roll or something. So great. So if this having a height of h, which is the minimum height of the block that we have to find out, then obviously this distance, if I take this line projected, then this distance is r minus h, since the radius is capital R. So we know this. Now since this angle is theta, this will be theta, this you know, and from the concept of free body diagram, we have done lots of problems on this kind of things in friction and rotational. Now what we have to do here, we have to find out, they have asked us to find h, the minimum height. So if I assume this is the minimum height where the weight, the vector weight is intersecting the sphere at a particular point, there is the weight which is holding the sphere. So this is under equilibrium, so weight is responsible for this kind of situation, and if it tupples, it will topple over this point only. It can be only topple through this point. Sure? Good. So now let us find out. Since this angle is theta, I have to somehow find out the value of h. Okay, so what was the concept? The concept is the sphere is resting on the block because of its weight, which is vertically downward, and that vector will intersect at a point, and that will be the point of concern for us. Okay, this is the concept. You see, it's a simple sum. It assumes to be very simple, but it is not. It has got a lot of concepts. It has got that thing that we never encountered. Okay, the weight, the vector weight is intersecting at a point on a sphere, and if I can restrict the sphere at that point, then only it won't fall. Now, from where this concept is coming, in lower classes 9, 10, we had a concept called center of gravity, and we say that the center of gravity for a uniform sphere is at the center. So weight will act, the total weight will act through the center, and this weight can provide the cylinder to slip or roll or topple. If it is restricted on this particular line, then only it will remain at equilibrium. You know that if you can find out the center of gravity of a particular extended body, you can even hold your finger like this and you can keep the object as it is without any other motion or without any imbalance, provided the surrounding is not affecting that particular extended body. We are considering that everything apart from the weight of center of gravity and the weight, vector weight, there is nothing in that particular extended body. Is that clear? Great. So now this is the concept. You see, so simple thing. We did it in class 9, 10. Alright. And now they are asking us to solve this problem in the entrance kind of thing. So here is simple. The solution will be of two lines, because we have the concept, everything is ready. This we know that, okay, fine, this is the point where we should keep the sphere at equilibrium. This is the only point because this is the line through which the weight is acting. Okay. So what I have to find? Let us find out cos theta here, because we have theta, we have r minus h, which is the base of this triangle. So what is the, and this angle is 90 degree, you can understand, this angle is 90 degree. So cos theta is r minus h by, obviously, the hypotenuse, which is capital R. Alright? So what is h equals to? You can understand. What is h equals to? Can you see this? Yes. H is equal to r minus r cos theta. So what is h finally? And I hope this particular expression was given in option D. Alright. So we have solved the problem. This is how we can actually think that what should be the way by which I can solve a problem. I'm telling you these kind of problems requires understanding. It requires the proper knowledge of all the concepts that a chapter has, or even the things we have done in our lower classes. Okay, sure, this is the thing. So correct option is D. Now you can see the result. Alright, Now we'll go to the next problem. You can see the diagram. I have drawn the diagram on the board. So M4, M3, M2, M1. This is the order they have given, and they have just given that this M4 is 48 kg. This they have given, and they have asked us to find this. They have not M2, M3 and other things. Anyways, so how many rods are there here? 1, 2, 3. One more information they have given, that all these rods are holding the next rod in certain ratio. Even all these strings are attached in this way. This is 1, this is 3. This is 1, this is 3. This is 1, this is 3. Okay, so this ratio they have given. Great. So this is kind that we have to, go like stairs. And first, let me tell you that what is the exact concept or what kind of thought process you should initiate when you see these kind of problems. I'm again telling you that here we have several rods. They have mentioned that these rods, they do not have any mass, or it is having these are having negligible masses. Great. So we are not going to concern anything about these rods. Fine. Now what next? They have said that this whole thing is under equilibrium. So none of them are having any rotational motion. And when you have this kind of arrangement, do you remember anything? Again, this problem is initiating a simple concept. What is that? What is the condition of equilibrium? What are the types of equilibrium we have? We have two types of equilibrium generally. We have other equilibriums, but I am not coming to them because those concepts will not be required for solving problems in rotational mechanics. In rotational mechanics, we are very much concerned about two motions. One is translatory motion, one is rotational motion. You see that in each and every concept, we have converted the linear thing into rotation. R cross F is tau, R cross mv is angular momentum, like this. That R is a very important factor. mv was the linear mechanics. Even the force was in linear mechanics. It was included in rotational mechanics, but we had to do torque, which is analogous to force, is R cross F. Angular momentum, which is analogous to linear momentum, is R cross linear momentum. Like that we imagine. Now, two types of equilibrium. One is translatory equilibrium. There is no scope of translation because it is held fixed through some rigid support. Great. So I can say whatever vertical weights is there, the net tension in the string will be that. That is fine. But the next thing is rotational equilibrium. So none of them are having or exhibiting any rotational mechanics. I mean, this is not going like this. This arrangement is not going like this. This is not going like this. Nothing is happening. So in order to fix the rotational equilibrium, what is the concept? The concept is principle of moment. That means total anti-clock moment is equal to total clock moment. This is so simple. It's so simple, and using this concept only we are going to solve this. Because now how you will understand that they are talking about equilibrium and they are thinking about the concept of principle of moment. Like in the previous term, the sphere was in equilibrium, but we applied something else. We applied the concept of center of gravity, and through which the vector of or the weight acts. That line was important. But here we will be thinking, okay, fine. We have moments because all these are weights which are vectors or force. So M1 and M2. If I just concentrate on this section, all of you, please concentrate on this section only. M2, M1, and they are pivoted here. And so this is the point through which they can have a rotational tendency. Sure? Great. So what I am going to write? I am going to write the very simple thing. What is that? M2 for this section, all of you. M2 into G, that is the weight. The weight is equal to moment of force into perpendicular distance. Since the forces and distances are mutually perpendicular, you need not to do any sin theta part or any cross product, you can directly write. Great. And what is this? M1G into 3. Okay. So what is M2 is 3M1. We have got one result. Okay. Great. So M2 is equal to 3M1. Now can you tell me what is the total weight hanging through this rod? Is M2 plus M1, and that is, what is the total weight here? This rod, for this rod, what is the total weight? M2 plus M1 into G. So M2 is 3M1. So total weight is 4M1. Okay? 4M1. Now, since we have got this, so let us forget this part, because we have already solved the equation for this part. Now what is this is there? What is hanging? You forget about the rod, forget everything. What is hanging here now? Can you tell me? 4M1. Sure. So again I can have a diagram. This is clock, anti-clock, sorry, and this is clock. So what I am going to write for this rod, what I am going to write? I am going to write that M3G into 1 is equal to 4M1G into 3. Okay, great. So what is M3 is 12M1, M2 3M1, M3 12M1. Great. So again, I hope you can understand that this portion is also solved. So what I am going to do? I will remove this section and I will just ignore as if this is not there. Forget. Nothing is here. There is one thing here. Can you tell me what? We have 12M1. So now we are close to the solved solution because we have M1 and M4. M4 I know, and the rest we can do. So what I am going to write again? Tell me. What I am going to write again? I am just removing all this. Okay, fine. Everything is gone. We have 4M1, M4. So what I am going to write? I am going to write M4 G into 1 is 12. Oh, one thing I missed. It is not 12, it should be 16 because there were two masses. I'm sorry. So 16 M1G into 3. Alright? So 48 M1 is equal to M4. So what is M1? Putting the value of M4 is 1 kg. So this is the solution. You can understand. We have just applied one concept. What is that? It is principle of moment of force, and that is it. Nothing is extra. We have solved one by one like the staircase, and the concept is simple, that we are restricting rotational motion. So we are applying the concept of rotational equilibrium, and that is equivalent to principle of moment, and we have solved the problem. The third problem, and this is very interesting. Here they have given that there is a plank which is moving with a velocity Vp. We are assuming that all these to be frictionless. They have not mentioned anything in the problem, and there is a cylinder on it which is performing pure rolling. I have marked this pure rolling because this is the point which we have to discuss. So they have asked what is the velocity at A. Okay, great. This is the problem. A cylinder is performing pure rolling on the plank which is moving with a uniform velocity Vp. What is the velocity of the point A? A is the point which is completely free with us. It is not touching the plank and all, and this cylinder is performing rolling motion. So it is rotating as well as it is moving forward. So why I have marked this pure rolling? Because of one thing. Let me draw the cylinder again, I mean the vertical cross section of cylinder again, because it is very important. We have 3 points for rolling motion which are very important, which is the center of mass VC. Do you know this concept? The center of mass is the only point in rolling motion which actually doesn't roll, it actually moves forward with a linear velocity Vc, so it exhibits the translatory motion. As you know, the trajectory of C will be a straight line. Good. But the rest of all other points on this particular cylinder, they are rolling. They are rotating. Sure, and they are also having translatory motion. So this is the fact. Now, tell me one thing. Here, see, if it is rolling in this fashion, let's say, like the way I marked here, I am also marking here, if it is rolling like this, then we have a velocity which is here, Vv, and we'll have a velocity here which is Va. Now can you tell me what is Vv equal to? Obviously, what is Vv equal to? Vv will be equal to, of course, the Vc is the linear velocity of this cylinder which is associated with the center of mass. They have mentioned, this is given, Vc and Vp only they have given. So what I can say about the velocity at V is Vc minus omega r. You see, omega is the angular speed, into r will give you the linear. So at this point, when it is rotating with omega, at this point we are having a velocity which is in this case like this. So we have to subtract whatever it is, I mean capital R or small r. So Vc minus omega r is Vv. This is what we have. Now what is Va? What is Va? We are going to that. Now tell me one thing. This Planck is also moving, right? So this, can I say that this Vv is a pseudo vector to Vp? Can I say this? Can I say this? It is the second important concept of rolling motion where we have a point touching another body which is moving. Please, please, please be careful. Can I say this? Yes, we can say this. Why? This is moving forward, this is having a velocity like this. If these two velocities are not equal and opposite, then the fundamental concept of rolling motion is violated. And what is that fundamental concept or the condition? That the point which is touching, momentarily touching any rigid support on which it is rolling. The cylinder is rolling over the Planck. That point should be at rest for an instant, because otherwise we won't get this torque to rotate. So if these two are not possessing this kind of thing, that they are equal and opposite, then the point B won't be at momentarily rest, at rest. It is very, very important. Please, please, please understand this. So what I am going to say now, we are going to say the simple thing. Vc minus omega r is equal to Vp, magnitude. Okay, so what is Vp? Okay, fine. So this is the relation. Now you see, this particular thing we do not have any relation. So what I can do is, we can just do like this. That this is equal to Vc minus Vp. Fine, keep it. So my point B consideration is over, and the concept is that B should be momentarily at rest, and that is the reason why the velocity of Planck and the velocity at B while it is rolling should be equal and opposite. They should be the kind of vector which will cancel each other, so that B will remain at rest momentarily. So this is the thing we have got applying this concept. Now next concept is very pretty simple. We will go for VA. What is VA? Is definitely, it is Vc. It should be there for rolling motion, and then since we are having this omega r in addition to Vc, then only they will come up, because this is momentarily at rest. So whatever thing is here, it should come up, addition, opposite to it. Please be careful. So we have the value of omega r. So what I am going to write, Va is equal to Vc minus 2Vc, Vc plus Vc minus Vp. So we have solved the problem. This would be the answer. This would be the answer. Okay, sure. If this surface is at rest, suppose this cylinder is rolling over ground, then eventually this relation, ignoring Vp, because then the Vp will be omitted. If Vp is not there, then this vector won't come. Can you understand this? Because you see, this problem is solved, but this doesn't mean that this problem is solved and this is going to come this year. They may ask you something which is based on this concept, and this is not the same sum. So it can roll on a surface. Okay, there are a lot of problems in hydrodromes and a lot of other books where they have actually cultivated this concept that Va is twice of Vc, since Vb should be at momentarily rest if it is rolling on a fixed surface. But since it is rolling on a moving plane, so this part is coming. Is that clear? Okay. So we are into solving the fourth problem, and as you have seen in the problem, this is again a concept of rolling motion. I did previous sum also that, but here we have very interesting thing, because we have two bodies connected by a plane, and they have asked us to find out the velocity of the center of the larger sphere, which is having a radius of 2r. This is having a radius which is r, and this is having a radius which is 2r. This was given in the problem. So this body is having a center of mass is having a velocity v. And just now we have understood this concept that this is moving on a fixed base. There is no plane which is moving below like it was before in the last sum. So here, in order to keep this momentarily rest, as I said, in rolling motion, the point of contact with the surface should be momentarily at rest, then only pure rolling can occur. Okay, so if it is V, eventually what I can write for A1, I mean this point, it is what? 2V. Great. So this we have now comfortable, right? Now let us come back to here. In this case, again this point has to be momentarily at rest. So if this velocity is 2v2 or whatever, then this should be 2v2 or something. If it is v2, then it will be 2v2. Okay, and the direction of rotation is like this, as we have mentioned here. Now what will be the angular velocity of this sphere? If say it is omega dash or something, what is the value of this omega dash? Omega dash is equal to v by r, and here lies the concept of solving this problem. Now what is that? We had a plank on it. It was connected on a plank, and when the plank is moving, they are rolling. So these 2 point of contacts, if they do not have similar velocity in the similar direction, then, or in dissimilar direction, whatever it is, but take the magnitude of the velocities of these 2 points which are actually in touch with the plank on its above, then there won't be any pure rolling, because if these two two are not having this velocity is equal in magnitude, then this pure rolling cannot occur because the plank cannot move forward in a proper way, and then the rolling won't occur. So obviously this value, what I can say, is definitely 2v. Okay, so eventually if we even don't find out this angular velocity, we can easily say what is v2. Can you tell me what is v2? Yes, it will be v. There is no other option for this. There is no other option for this. This will be v. If they are connected by a plank on the top of it, then it will be v, because it has to be 2v. And we know for pure rolling, if this is 2v, this is v, and this is 0, then only this can occur. Alright? So this is the solution of the problem. And you see, did we actually did we do any mathematics? No. Using the concept we have solved this problem, and if it is there, as you have seen in the diagram, it was so we thought, okay, this is a tough problem, but it is not a tough problem because we know the concept. Within few seconds we can answer this. Alright, so please remember this kind of problems or these concepts. I usually don't advise you to remember problems, but what I do is to remember the concepts that you have applied in solving this problem, because that is going to help you, because this problem won't come, but the concept will come. Alright? So we are into the fifth problem, and this, I'm telling you, is the most interesting part, or the most interesting sum, or the interesting concept that we are going to map. The situation they have depicted is about a collision of a sphere which was initially rolling. This was frictionless and it is colliding with the edge. And the interesting is that after collision, what they have said, that their angular velocity is 0. That means now it is no more rolling. So it has a collision and now it is coming as if it is sliding with certain velocity v dash. I have drawn the diagram after collision. This was the situation that is given before collision, and this diagram was there in the given problem. This is after collision. So what they are saying, the center of mass is moving with a velocity v dash. We have omega dash which is 0, and the most interesting concept which this sum is all about, the part here, since we are talking about collision, so there will be certain change in velocity, there will be certain things. So whenever there is a change in velocity or change in momentum, linear momentum, so change in linear momentum, this particular phrase indicates to what? Indicates to impulse. So we have two impulses here. One is in the horizontal direction, obviously, because it is going and it is coming back. So there is a horizontal change. But the interesting fact is we have a friction on the edge, and friction, when it is colliding, the normal reaction with respect to the edge is definitely, you can say this normal reaction is this. The edge, what is edge is given to the sphere is n, if I say. Then this normal reaction will have certain frictional force upward. Now why this frictional force is upward? Because at the time of collision, see this diagram, at the time of collision it is rolling, it is hitting. So at the time of collision, the tendency of the point which is hitting the edge is rotating this way. So here it is rotating this way. That means the frictional force will act upward. So this is the vertical change in impulse, because the friction will provide certain things that will come up here. So we have to think with respect to impulse, which is equal to the change in momentum. It can be linear, like after collision it is moving linearly. So we have a linear change in impulse which is horizontally, But at the time of collision and after collision, when it is leaving the edge and coming back, at that point of time, till the point the friction was there and frictional force directed upward, and you know that impulse is also equal to force into small duration of time. So you see how magnificent is this one. I mean, what I am trying to say, that how they have incorporated the simple concept in this one problem. No one even thought, okay, we have to think about impulse in rotational mechanics in this way. We have a horizontal part, we have a vertical part, because friction is there, and that friction is acting for a very small duration. So there also the impulse is there as per the definition of impulse. And whenever there is a change in velocity, the change in linear momentum, there is impulse. So here also the impulse is acting in the horizontal direction. So these are the concepts, my dear students, that we have to think, and that's why I am telling you this is amazing. I mean, in one sum you have to think so many concepts that it is going to give you an immense idea. Okay, fine, how I can solve, or what are the solving methods in rotational mechanics which I have to apply. So you have now a new way that even you have to think about the impulse if there is a change in linear momentum or there is change in some angular momentum also. Here the linear velocity and the angular velocity both are changing. So we have two different impulse, that is linear one, the linear change in velocity, as well as the rotational one. Previously it was omega, now it is 0. It is no more rolling, it is no more rotating. So what happens? What caused the rotation to get stopped is the frictional force, and that's why we have to think an impulse with respect to the frictional force. So this is the logic, these are the concepts, and these are the logic behind the concepts. Why I am thinking, why I am at all thinking about all this? Because there are logics behind it. Okay? So now, since we have understood the logic, so now it will take 2-3 lines to solve the problem, because in physics, I was telling you that this particular class is all about to understand the concepts that we are going to use while solving problems. We know everything apparently, but when it comes to solving problems, then it becomes so clumsy. We are very narrow now, but don't think like that. We have this concept, we have to think that how we can solve this problem. Here the thought process is collision. Collision means change in momentum. Linear, fine, we have a linear impulse. Rotational, fine, we have mentioned that angular velocity is 0. So there is a rotational impulse, angular momentum also changing. So we have a rotational impulse. And who is providing? Who is causing this omega to be equal to 0? Friction. So we have to think about the friction which is acting for a small duration of time. Just the point of touch and back. So that's it. Okay. So first this one, horizontal one, what I am going to write? I am going to write something. Let us write in the normal form, the normal way we write. We have the normal here, which is horizontal. So n dt, large force acting for a small duration of time. The impact goes and back like that. And what is that? This side is negative, that is positive, you know. So minus mv dash minus mv. Fine, this is equation 1. What about the next one? JB. Who is causing? Frictional force. Okay. Frictional force. What is frictional force? What is frictional force? Mu n or mu r. I mean, we are not using r because we have radius and other things. So forget. N into dt. Mu n dt. Okay. Mu n dt. Now mu n dt. This is linear impulse, right? So what is rotational? What do we know? Radius and friction is perpendicular to each other. So what do you know? R cross. So mu r This R is coming because this is rotational, this is angular. I'm again telling you, this was linear, this is angular. And then NDT. Actually it is mu NDT and then R is here. And what does it is equal to? Change in momentum. No? Okay. So what was the initial momentum and what is the final? 0. I am writing in this fashion, no issue. So since frictional force is non-conservative, so it is negative becoming positive. So that way. Alright, so what I am going to write, mu r integration in dt is equal to what? I omega sphere 2 by 5 whatever m r square, and omega is, you see in the sum they had mentioned this b equals to capital R omega or something, so we are replacing it. Now this equation and this equation, if I think, you see R get cancelled, here is also R get cancelled. What is the value of mu? 1 by 5. So what I am going to write next, this is 1 by 5, entity is as it is, leave it because this is for the vertical one, equals to 2 by 5. So 1 by 5, 5 cancel, R square cancel. So what remains? We are getting n dt equals to 2mv. This I am getting, and we also have this. We have this, we have this. What does it suggest? It suggests that linear change of momentum is 2mv, and what it suggests, the linear change of momentum is mv dash minus mv. If this is equal to this, then what necessarily we can conclude? We need not to solve, we need not to think, we can easily say. Because if this is equal to this, then v dash has to be equal to, these negative signs are for the sign convention, that is not an issue. So you see how we have to think with respect to certain problems that we had here, and it is so interesting, so amazing that we are applying impulse, the concept of impulse in rotational mechanics, because it is a combination of collision, rotational mechanics, and after that, after collision is linear, because it is no more rotating. So that's it. So this is the solution. I hope you have understood this, and please, I'm telling you, this is a gem of concept. So many things are incorporated in one single sum. So please don't ignore. Practice this, understand this, and think how many different cases we can apply this kind of situation. Jot it down. So now we are on the last problem of this half a dozen, and this is very interesting. Let us assume that this center of mass is having an angular velocity which is omega and the linear velocity is v. Then what will be the relation? It will be v by 2r. Now why it is 2r? Because this center and from here the distance is 2r, so rotational radius I can say. If it is connected with this, I am sure about it, but I am talking about till 2 because it is rolling. It is rolling. So 2r, not r. Okay. So what is the kinetic energy of this system? Obviously we have a linear velocity, so linear kinetic energy is half mv square. Great. And then half I, which is, it is given in the problem, and then omega square. So v square by 4r square. So if you cancel all this, you will probably get half mv square here, 4 and 2 will get cancelled, r square will get cancelled. So half into 1 by 4 mv square and something, and this is this. So it is 3 by 4 mv square. Okay. So this is the kinetic energy of this system. And they have asked us to find out the ratio for the kinetic energy of the system and this block. So what about this block? What I can say about this block? The block is falling down with a velocity which is the velocity of this stream, whatever it is, say v dash, or whatever. This is the velocity of the center of mass, and v dash is the velocity of this. So what I can actually say, what is this v dash? Can you tell me? It's simple, you know, from this point which is momentarily at rest, if I go up, it is revolving with omega, that is given. So if I go up, now why I am not writing if this is V, this is 2V, because this is not the free section, there is another here also. So that's why you have to understand this. So what is V dash? The V dash is the velocity of this end, which is directed along the stream, because it is the stream which is moving, and that is the reason why this block is moving now. So this point till this point, what is the distance? 3r. So what I can say, V dash is equal to omega into 3r. So we have this. Now we have omega. What is that? V by 2r, and this is 3r. So what I am getting finally? I am getting 3v by 2. So what is the kinetic energy of the block? Half m v dash square, which is alright. So need I have to tell you the answer? Yeah. What I am getting? This is 3 by 4 mv square, and this is 9 by 8 mv square. So dividing, what I am going to get is definitely, so this is the answer. Clear? You see, was it difficult? No, it wasn't difficult, but now you can have a question that why we only thought about the omega, why I am not thinking about v and other things. Because v is the velocity of the center of mass. There are two bodies which are incorporated, one is connected, other is free. So when this revolves, this will automatically revolve, and this is the contact point. So which is actually revolving, that is not in contact with the fixed support, and that is the reason why this particular step is important. Is that clear? So please understand why we have taken this kind of thing. And when they ask you that find the kinetic energy of a rolling motion, you know already it is translational plus rotational. So the rest of the concepts are easy, but the only thing is to visualize this part. Alright? Sure. So here I have concluded this class, which is based on rotational mechanics. I did 6 problems with you, that is half a dozen as I named it. So this is what we have. Now this is the revision of class 11. As we have ample amount of time right now, we can revise the concepts that we had in class 11, and I think this will again give you the brainstorm that you can think that in what direction you have to think when we have problems like this in your entrance. And I am telling you, I told you a lot of times that rotational mechanics is a very favorite section for the examiners, because the question paper, when they say, they always try to find some sort of incorporation of concepts, and that is very much feasible for rotational mechanics because it is having a lot of variety, and we have done 6 varieties, and in these 6 varieties I have tried you to understand the different layers of rotational mechanics. Alright, we'll come up with these type of classes like half a dozen with other topics, as well as for the rotational again we'll do other problems. So right now it's now your turn. Do solve this problem and do practice this problem and try to understand that what is the exact methodology for problem solving in rotational mechanics. Okay, so till then, goodbye, stay safe and stay productive.